Okay, this is the second section of ideal gas law, and this is more of an applications of the ideal gas law. Okay, and so we can calculate density from the gas law. Okay, so this is derived from the gas law and the fact that the ideal gas law is pressure times volume is equal to nRT. Okay, N, as I showed in the previous video, is mass divided by molar mass. So if I substitute that in, pressure volume is equal to mass divided by molar mass, RT. Get rid of the fractions, so I have pressure times volume times molar mass is mass, RT. And then I divide both sides by the volume, so I get pressure molar mass is equal to mass divided by V, RT. And then mass, and then density, is mass divided by volume. Okay, so basically this is still the same ideal gas law. We just have rearranged it to get molar mass out and density. Okay, and so if you know the density or you know the mass and the volume, you can also calculate the molar mass of a gas. Okay, so let's do some problems with that. Okay, it says calculate the density of ammonia gas at 31 degrees C and 751 atmospheres. Obtain the densities in grams per liter, which is what it comes out to be from the ideal gas law. Okay, so it wants to know what is the density. I have ammonia gas. I have 31 degrees C, which is my temperature. And I have 751 millimeters of mercury, which is a representation of my pressure. Okay, and so the equation with density, temperature, and pressure is that, pressure times molar mass is equal to density, RT. Okay, the pressure has to still be in 1 atmosphere, so I'm going to divide by 760, just like we did in the previous problem. And when I do that, I get 0.9882 atmospheres. The molar mass, so the molar mass of NH3 is 14.01 for nitrogen plus 3 times the 1.01 for hydrogen to give me 17.01. Density is what I'm looking for. R is 0.0821. And my temperature has to be in Kelvin, so I have to add my 273 to this. And I get 304 K. Alright. So when I plug these in, I get 0.9882 times my 17.04 is equal to density, which is what I'm going to solve for, times 0.0821 and 304 K. Okay, so I multiply these two terms together and I get 16.838. I multiply those two terms together and I get 24.958D. So I divide both sides by 24.958. So my density is 16.838 divided by 24.958, and that is 0.6 675, and the units are grams per liter. Okay, so that's what you have to do to that one. All right. Oops. I'm going to switch color. Okay. Again, I really suggest that you stop and try this problem on your own before you watch me work it. Okay. Similar problem. Okay. You vaporize a liquid substance at 100 degrees Celsius and 755 millimeters of mercury. The volume of 0.548 grams of the vapor is 237 milliliters. What is the molecular mass of the substance? Okay, so I have 100 degrees C, which is represented by T. I have 755 millimeters of mercury, which is represented by P. I have 0.548 grams, which is my mass. And I have 237 milliliters, which is my volume. So I have one temperature, one pressure, one volume. And it wants to know what is the molar mass. Okay. So again, I have pressure times molar mass is equal to density RT. Okay, the pressure still has to be in millimeters, or in atmosphere, sorry, so I have to divide by 760. And I get 0.9934 atmospheres. The molar mass is what I'm solving for. Density is mass divided by volume, but the volume has to be in liters. Okay, so I divide by 1,000, or move the decimal places 3 to the left, 237 liters. So the density is 0.548 divided by 0.237, and that gives me 2.312 grams per liter. R is the constant. R is 0.0821, and my temperature has to be in Kelvin, so I add 273 to get 373 K. Okay, so I start plugging it in, and I have 0.9934, that's a 4, times the molar mass is equal to 2.312 times that 0.0821 times 373. Okay, so this just becomes 0.9934 mm. When I multiply these three terms together, I get 70.808. I divide both sides now by the 0.934. And so my molar mass is 71.3 grams per mole. Okay, so that's one way of doing this. Okay, another way of doing this is that I can still use the ideal gas law. Okay, so the difference is that I had to first calculate density before I could plug it in. If I use the ideal gas law straight, then I calculate in and then find the molar mass from that. Okay. I don't know that I have enough room here, but we'll see. Okay, switch colors. So using the ideal gas law, PV is equal to nRT. So I still have 0.9934, but my volume was 0.250. N is what I don't know. R is 0.0821, and temperature is 304. Oops, 373. 304 was an old problem. So I multiply these two terms together and I get 0.2354. I multiply these two terms together and I get 30.62 N. So I divide both sides by 30.62. So N is equal to 0.007688 moles. Okay, but that's not what it was actually asking for. It was asking for the molar mass. So if I take N is equal to mass divided by molar mass, multiply both sides by molar mass first, so N times molar mass, use parentheses instead, is equal to mass, and then molar mass is mass divided by N. So my molar mass is equal to my 0.548 grams divided by my N, which was 0.007688, to give me still 71.3 grams per mole. Okay, so in this way, I had to first calculate my density and then plug in my density. If I did this way, I didn't have to do anything prior other than changing my units of temperature and volume. Okay, I solved for N, and then once I had N, I solved for molar mass. Okay, and I got grams per mole. I did realize I kind of switched ways of doing this in the middle. Let me go back real quick. Okay, so N is 0.007688 is equal to this 0.548 over molar mass. I still have to multiply molar mass on both sides, so I get 0.007688 molar mass is equal to 0.548. Then I divide both sides here to get molar mass and 71.33. Okay? Alright, and this is the end of the second video.